again. I noticed to my delight that the video focused on visual shaders seemed pretty popular, which led me to the idea that I could delve into this topic more often. In today's video, we will once again be playing with graphs, and this time we'll show something a little different, something that you can already see on this screen. It might look complicated, but the algorithm for generating the effect is actually very simple. Let's do it. Last time, we were able to enhance a 3D model, more precisely its material. Today, for change, we'll move to the 2D plane, where we'll attempt to generate various interesting patterns based on mathematical functions and calculations. So, there's no need to have anything prepared, and we'll dive straight into work. As usual, we'll start with a new 2D scene, to which we'll add a canvas layer and a color rack as a child node. Let's do it. 2D scene, right-click, add child node, canvas layer, right-click, add child node, color rack, and then want this color rack to fill the whole viewport. So in layout, we'll just select full rack and anchors preset. And we have to add a material. It would be a new canvas item. It would be a new shader material, of course. Click the material, and for the shader, we'll select new shader and make sure that it's a visual shader and canvas item. Let's put it to shaders folder, and I'll call it, for example, I don't know, effect for now. Open and create. Great. First and foremost, we want to achieve the same effect regardless of the viewport size, so we will start by implementing coordinate conversion. We will use a graph to model the following formula. As you can see on the screen, vector is screen UV minus 0.5 divided by the aspect ratio of the pixel size, and the y-coordinate is 1.0. I think we already used that in some of our previous videos, so the idea is always the same. Notice this constant 0.5. Since screen UV coordinates range from 0 to 1, this operation will shift the origin 0.00 to the center of the viewport. This will be very advantageous for creating our symmetrical ornament. Of course, if you don't mind this detail, you can skip the previous step and work directly with UV is simply equal to screen UV. Okay, let's start. I will find our shader file. It's here, effect, double click to open the visual shader editor. Let's make it a bit bigger. And we need first we need a vector op to make the subtraction of vectors. It would be vector 2, and the first argument is screen UV, so we can simply find it here, screen UV, and drag it here as the first argument, and the second one is simply a constant 0.5. This is a vector, so we'll make it like this, float, just not to put it there twice. Float constant is 0.5 and drag it to that. So this is the first part of the formula I showed on the screen before, and now we need the second part. So first the aspect ratio, so we will have another float up. Here it's float up, and it is a division, and we want to divide again, it's screen pixel size, I think, screen pixel size, and we'll do it twice. because we want to divide the first argument, it is like red here, and the second argument green. So this is the division, and I guess we need to create a vector out of that because the y coordinates was 1. So I'll add vector compose for vector 2. The x part is this one, and the y would be equal to 1. Very well, and let's make the final vector op. These two arguments were divided, so I'll add it here as a vector op, vector 2, and divide the first one divided by the second one. Great! The preparatory work is complete and we can begin with the creation. The foundation of our algorithm will be the length of the UV vector for the coordinates of the current fragment. Because the length is calculated as a distance from the point to the origin, which we shifted to the center, it will be displayed as a radial gradient from the center to the edges of the viewport. So we have to add a length of vector, len 2D, okay, and just connect this output and this. Okay, nothing happened. Why is that? Let's verify. Ah, sure. As I said, we need to subtract 0.5 and we have add here. Let's fix it. And now it works. Good. We are slowly getting to the core of our effect, which involves iterations. Now, we'll take the UV vector and, before calculating its length, we'll perform repeated transformations of its value. This means we need to add a loop, something like for int e equals 0, e less than 10, e++, which ensures that the sequence of operations in this block is executed 10 times in a row. You're probably familiar with this from GDScript or other programming languages. As far as I know, visual shaders do not directly support something like this. If I'm mistaken, please let me know in the comments. So we'll use a node called expression to help us. An expression node must have an input and an output. Let me just expand this and I'll add it over here. I'll put it there and right click, add no expression. Okay, and we will add one input, which would be a vector 2, because we'll set it as the output from our previous graph, which is a vector 2 as well. And the output, let's call it vector 2 again, let's call it result. Okay, just a minute, I'll make more space here, and let's put it here, and I'll connect the output to our vector length. Okay, of course nothing is displayed here because there is no expression yet. We need to add it. By the way, adding the output immediately created a variable in the code, so we can use result right at the end of the algorithm. Let's expand this expression and I will write the code for int, 0 e less than 10, so we repeat it 10 times. Okay, yeah, here. And let's start with doing nothing, so UV would be simply UV. And as last line, result is our final UV value. Okay, yeah, nothing is here because we have some kind of error. Oh, maybe not. Yeah, unknown identifier UV. Of course, I forgot to rename that. Sorry again. Here it goes. And it works now. Great. Okay, let's improve it a little bit. I'll just zoom in and we will subtract something from the vector. Let's say 0. minus 0.01. Yeah, it shifted a little bit, right? On both axes, because we are subtracting float from vector, which means it will be subtracted from both components, x and y. Okay. We'll try replacing UV with its absolute value. Abs UV. And we are getting to something new. Let's take a look. Because negative values were changed to positive ones. So we can see that the result exhibits symmetric properties, especially after we increase the subtracted constant to, let's say, 0.5. 0.5? Yeah. Now it's different. However, it's not quite what we want, so we'll continue with modifications, and this time we'll multiply each iteration by a coefficient, let's say 1.2. So we put it to brackets and multiply by 1.2. A pattern is starting to emerge. To add even more transformations depending on the coordinates of a specific point, we'll introduce a two-dimensional rotation. This is a good opportunity to use the second of the graph nodes we haven't utilized yet, namely global expression. Thanks to this, we can declare a function that we will then call from anywhere in our shader. So I'll zoom out and create a new node here, right-click and global expression. Okay, and let me zoom in again and write it here. This is a well-known algorithm for rotating a point in 2D plane, so I won't just explain a little bit. It can be found anywhere on Wikipedia, for example. Let's just type it. Vec rotate and arguments vec2 UV float angle. I'll make it a little bigger, like this. Alright, and we return UV multiplied by a two-dimensional matrix, which will be defined by vectors. First vector 2 is cosine angle and minus sine angle. Okay, and the second vector sine angle, cosine angle. Alright, this should be correct. And let's apply this new function to our other expression. It would be here, so we will simply call rotate this, and we need to define an angle, so let's just write it here, and we need a new input parameter. This time it would be a float called angle, and let's add some temporary value into that. I'll add it here as float constant 0.5, for example. Okay, so this is definitely something much closer to the desired effect. By the way, conventional wisdom, especially among old school coders, suggests that trigonometric functions are computationally expensive and should be avoided, often through the use of lookup tables or approximations. While this advice remains valid in specific scenarios such as CPU-intensive inner loops, it doesn't hold true in general. For instance, on the GPU, calculating a cosine function is significantly faster than attempting any form of approximation. Therefore, don't be afraid of using these functions in your shaders and always try to leverage this advantage. Very well, let's change the angle and observe different deformations. So, for instance, if we change it to 0.1, that's something completely different looking. Or what if it's 1? Yeah. 2. Very similar. Let's stick to 0.5. Okay, and it would be great if we can add a motion to our pattern, so the angle can be controlled by the internal timer. Let me add, instead of this constant, a time node and connect it. So I'll delete that and add time. Okay, and if we simply connect that, yeah, it's moving, but it's too fast. So I would make it a little slower by adding another float operation here. Float up, that would be multiplication by a small constant, for example 0.1, and connect. That's better. I think we should definitely change some of these constants, like this 10 or 0.5, 1.2, into uniform variables. Let's do it for Let's do it for iteration speed, subtract and multiply. So I'll use this small trick to get more space for this. First, let's get rid of the distractions, and now click here to put the graph editor to the whole screen. Alright, so as I was saying, we want to add a uniform parameter. That would be parameter, which is, let's start with iterations, it's integer, and let's call it iterations. Nothing else is here, maybe some default value, which would be 10, as we already have it here. And we'll add input here as int iterations. Let's connect. It might be better if I move everything to this side. Now I can connect the iterations to this and replace it here, iterations. Okay, let's just check it's still working. It does. It is. Sorry. Okay, first, this is the first one. Now we want to change this, so I will call it subtract, and this is a float, right? So float parameter, subtract, and again default value, let's set to 0.5, and we have to add input, which is float, subtract. It looks a bit tedious, but thanks to this we'll be able to modify all these parameters in real time through the inspector. So it's definitely worth a little typing. Subtract. Okay, and the multiplicator, another float parameter, multiply with default value 1.2, add input as float, multiply, connect, let's expand, multiply. Is that everything? Almost. Let's just verify, it's still moving. Good. One last thing, we are using a multiplicator for the time, which is constant. Let's call it speed as another float parameter. Float parameter, speed, default value would be 0.1, and this time we can simply connect that here. Yeah, works nice. Okay. I think we can add one more parameter, which we'll call zoom. So let's do it, for instance, here. It would be, again, the parameter of float type, zoom, and we definitely want to make sure that the zoom isn't 0 because we'll be dividing by that. So let's add a range as a hint from 0.1 to, I don't know, 5. Okay, and the default value would be 1, like there's no zoom. Alright, I think the graph will require some rearranging after we are finished, so let's just put it anywhere and I'll fix it later. And we want to apply it here at this part, so let's add another vector up for vector 2, and this operation would be a division. Let's divide our vector UV, which is here, by zoom factor, and the result would be fed to the expression. Let's take a look. Yes, nothing is broken so far, so let's get back to our previous view, and now we should be able to find the parameters and change them. So let's select the color rack in our scene, which would have the parameter, and we have shader parameters here. What happens if we play with zoom, for instance? Yeah, it's zooming in, out. Great, let's get back, change the speed. I think we should add hint ranges here as well, because there is no slider, but this is a simple way to improve. Increasing iterations, decreasing iterations, and these values subtract and multiply. You can achieve a lot, plenty of various effects if you just fine-tune them. The ornament looks nice, but it lacks color. Everything is displayed in shades of gray. To address this issue, we will employ a well-known algorithm for generating a color palette based on several input parameters. I will do it as another global expression and then connect it to a new expression just to save some time and space, because doing everything with nodes can be, less convenient than we would like to. So let's make some space again, and this time we will create a global expression. Let's say here, right click, expression, global expression, and it would be this algorithm, vec3, palette, and float t, which we will set to the time variable multiplied by speed as before, and then now 4 colors: vec3 color A, vec3 B, vec3 C, and vec3 D. Okay, and the calculation is return A plus B multiplied by cosine 2.0 by pi times C times T plus D, and finish the brackets. Yeah, that's it. Very well, this is the function. Now we need to use it, and we will also define 4 more uniform parameters to specify these 4 colors in the inspector, so we can modify the palette as well. I will move these to nodes to the right side to make space for a new expression. First, of course, for the input parameters uniforms. So add node, color parameter, there it is. Let's call it color A, and the default value would be 0.5, 0.5, 0.5. This palette is actually a result of my exploration of a specific site that provides various combinations of these four parameters and the resulting palette. So I think I liked this one the most. Color B has the same default value, Control D, color C, and this one would be 1.5, so it's some kind of yellow. And let's make space for the fourth one, Control D, color D, and the default value is, this time it's 0.8, 0.9 and 0.3. Very well. It's time to add the expression. Right click, expression, and we will need input variables, of course. So it would be, what's that? It's vector 3, right? So this is correct. And let's call it color A, and do it 4 more times. Color B, color C, and color D. All right, and of course we need to have input as an output from the previous expression, which is vector 2. So let's add a vector 2, and again we'll call it UV, as we are still working with that. And the output, I think the output can be called result again, no problem. At least we keep it consistent. Still a little more time here. And now, of course, the expression itself. So I think we can do this. Let's call create vector 3, call it P, because we were using the palette function. Palette and we will use the length UV from this node, but I don't want to incorporate it in some complicated way into the expression. Not sure if it's even possible, so let's just put it here, no problem. Length UV, and these colors, color A, let's just copy, color B, color C, color D. Okay, and we need to include this newly created vector P to our color calculation. And since we'll be doing more modifications, let's make sure that the final value won't fall outside the 0 to 1 range. So this will be our result. It is no longer, yeah, it's still vector 3, it is correct. So let's say that the result is, and as I said, we want to clamp it to the range, so we will call the function clamp and vec3 from the length UV. What did I? It's too small, sorry. Length UV multiplied by our palette value and the boundaries vec3 0 and vec3 1. All right. So now the output is no longer UV, but it's the color, so we don't need vectorland anymore. Instead, we will connect this output to this input, and the result, which is vector 3, the color, we put here. And let's not forget that the uniforms must be connected actually to the expression, otherwise there's nothing to calculate with. So, yeah, color A, 1, color B, 2, color 3, and color 4 or D. Let's take a look. Yeah, you can see some nice colors here. So I suppose that the algorithm looks correct. Great. Not bad. We can improve the color effect on the edges by adding a dot product here to the calculation. So in this palette, let's to length UV add plus dot UV and UV. Dot, of course. UV and UV. Okay. And take a look. Effect is definitely different, and I think that the contrast is better as well. One last thing, to improve the contrast of certain pattern variations, let me add another set of graph nodes to compute an inverted color. Or more like, I think that it's not necessary to make it from graph nodes. Let's add another global expression. So that would be, for example, here, right click, global expression, and we'll add one more function, vector 3, invert color, that takes vector 3 color as a parameter, and float intensity. Okay. And what we want to do here is to return a simple mix, like linear interpolation as we know it from GD script, and we take the RGB component of the color and mix it with the same subtracted from 1, so it's color RGB, and the weight coefficient would be the intensity. Okay, that's all. And let's add it to the algorithm with a variable mix intensity. So how can we do that? I think we will change the result once more, and let's define this. Float intensity is to make it more variable. Let's add the time, and of course we'll need the time here as an input parameter. So let's call it T for simplicity, and I would multiply that by 0.25 and subtract 0.2. Again, I've been experimenting, and this is the result, nothing to it. And the result would be then invert color with our current result and the intensity. Okay, and let's not forget to add the input. That would be float, we called it T, and where is this time? Over there. It's too far away. Let's just okay, I will connect it anyway. Let's take a look. Maybe there is a change, maybe not. I think there is something, because the colors look more colorful, I would say. Okay, and that's it. I think the original ornament looked a bit different. It was greener and with some cyclic zoom modifications, but I guess that I simply used slightly different parameters. Our graph has grown a bit, but the final effect was definitely worth it. Of course, if we were to write the same shader using shading language, the resulting code would be significantly shorter than what the graph ultimately generated. However, a graph can be more visual and easier for some to understand. Anyway, I hope you enjoyed the video, and I look forward to sharing new effects and tricks with you again sometime in the future.